Okay, so hi everyone. So today in this video we are going to solve this problem from CSES problem set that comes under the sliding window section, and the name of the problem is sliding window max, right? So let us start with this problem now. So the problem reads like this, that you are given an array of n integers and your task is to calculate the max of each window of k elements from left to right. So here is the definition of max written. So the max is the smallest non-negative integer that does not appear in the array. For example, the max of this array here is 2, right? So in the input, the first line contains two integers n and k representing the number of elements and the size of the window, and then there are n integers, that is the content of the array. In the output you have to print n minus k plus 1 values, that is the max value for each window. And since the total number of windows will be n minus k plus 1, that's why you have to print n minus k plus 1 values. And here are the constraints, and this is a given example, and this is the expected output, right? So this is the problem, and the problem is asking you to do a simple thing, that for each of the window of fixed size k you have to print the MEX value, that is the minimum excluded value of that window. So let us now move forward and try to see how we will solve this problem. This is the given array, right? So I have took the same example as given in the problem, right? So this is the given input, right, in which a total of 8 elements are present, that is n is equal to 8, and a window size of fixed size k equal to 3 is also given, right? So for each window, which would start from the first index here, because I want to use it as a one based indexing, so that's why I have added a 0 here as a dummy value, right? So it is not actually given, I have considered it. So our actual array as given in the input only starts from this and goes all the way till this, right? So now we know that the total number of windows that are present is nothing but 6, that is n minus k plus 1, that is 8 minus 3 plus 1, right? So a total of 6 windows are present here, and for each window that I have marked with different colors here, as you can see, we have to find the max value, that is the minimum excluded value of that window, right? So here this is our first window which contains these elements, and for this window the MEX value is nothing but 0, that is the expected value. Similarly, for the second window the expected MEX value is 3, for the third window it is 2, for the fourth window it is also 2, for the fifth window it is again 0, and for the last window it is 2, right? So these are the expected MEX values for each of the windows, starting from the first window and going till the last sixth window. I want you to observe something here. So it is clearly visible that the answer for each of the window is either here 0 or 2 or 3 here. In short, the answer for each of the window is always less than or equal to this k, right? It is never exceeding this k, and it is not just a coincidence, it is actually true. But why? So let us see that. So in the question it is written that MEX value is nothing but the smallest non-negative integer that is not present in the array, right? That is, our possible max values can start from 0 and will go like this, that is either 0 or 1 or 2 and so on, right? So these can be the possible max values of any window that is a non-negative integer, and we have to find the smallest out of it. Now what I am saying is, since we have observed one thing, that the max of each of the window here is less than or equal to k, so let us see that why is it so. So I am dividing the answer for each of the window into two cases, right? So this is case 1 and this is case 2. What I am saying is, since we have a fixed window here of size 3 every time, and in that window there will be 3 elements present, right? So those 3 elements can either be same or distinct or in any combination, right? So if all such elements of a k-sized window are distinct, right, that is no element is repeated at all, and they are taken from the start of what? Start of this range, then what will be the max? So max will be nothing but k in that case, right? So since here the window size is 3, so for any window of size 3, if you want to fill it with 3 elements and you pick it from the start of this whole numbers, that is these three elements, then in that case our max will be nothing but the smallest non-negative integer present in that window, right? Which will be 3 in that case, right? So our max answer will be 3 here. I hope you got this, what I just did. So what I'm saying is very simple, that if you have a fixed size window of size k and you fill it with all the distinct elements which are taken from the start of this whole numbers, then the element just after the last one which you selected will be our MEX value, because this is the smallest non-negative integer which is missing in this window, right? Also 4 is missing, 5 is missing, 6 is missing, but 3 is the smallest which is missing in this window. So that's why 3 will be our max, and we have to print this 3, right? So this is the case 1 when all elements are distinct and are taken from the start. But if you try to change any element of this 3 size window into any other element, let's say we decided to change this 0 into some another value like 3 or 4 or 1 or 2 or any other, right? Similarly, if you try to change this 1 to any other value, similarly if you try to change this 2 to any another value, then in either of the case your MEX value for that window will always lie in this range only, right? So you can see it here also. So if I tell you here, then suppose what we did, we changed this 0, let's say, into 3. Now someone if asks you to tell the MEX value, then we know that in this window 0 is missing, right? So that's why 0 will be the MEX value in this case, which is less than or equal to 2, right? Similarly, instead of this changing this 0 to 3, if we decided to change this one to any another value, let's say we decided to change this one into, let's say, 2 only, then again the smallest non-negative integer that is missing here is nothing but 1, which is again less than or equal to this 2, right? Similarly, if you try to change this 2 into any another value, let's say I changed it to 77, right? So again the smallest non-negative integer that is missing here is nothing but 2, because after 1 77 is coming. So 2 is the smallest non-negative integer which is missing here. So this is what I am trying to say, that this will be our case 2, that for a window if not all elements are distinct and are not taken from the start, that is if any one of the elements will change at least to any another value, then the MEX value of that window will always be less than or equal to k minus 1 in that case, right? As we saw here that it was always less than or equal to 2. So that's why I can say that the maximum value of MEX will be equal to k, and it will take place when all the elements will be distinct and will be taken from the start, right? But if any one of the value of that window changes, then our MEX value always lies in this range, that is less than or equal to k minus 1. So that's why if we have to define a range for a MEX, then it will always be greater than or equal to 0, and it will always be less than or equal to k for any window, right? That is, the total possible max values will lie in this range, that is 0 to k. And since here the k is equal to 3, so that's why 0 to 3, that is 0 or 1 or 2 or 3. So that's why I can say that our answer for every window lies in this range, that is 0 to k. So our answer for every window will either be 0 or 1 or 2 or 3. And why it will happen, I just showed you here, because for every window it will either belong to this case or this case. So if you see here, then this is the first window in which 2 1 are present and 1 2 is present. So all elements are not distinct, and since all elements are not distinct, it belongs to the case 2. But here if you see the second window, then these are the elements present here, that is 0 and 1 and 2. So a fixed size window of size 3, and it is containing the elements from the start, that is 0 and 1 and 2. So that's why our max will be this value, that is 3, that is the value of k. So that's why the answer for the second window here is 3, that is it belongs to the case 1. Similarly, if you see here the third window, so it comprises of these elements, right? That is 0 and 1 and 5. So it means that it also belongs to the case 2, right? So this is the concept here. The core logic of this here is to make you understand that the max value for each and every window here will be greater than or equal to 0, and it will be less than or equal to k, that is from 0 to k, that is from 0 to 3, right? So that's why in the output also the answer for each of the window here is from 0 to 3 only, right? So it will never exceed this 3. And why it happened, I just showed you mathematically. Because if any integer is missing from this range, then it will become the max value, and that's why it will never go searching in this range. And if every value is present, then this will be our max value, right? So that's why our possible max value only lies in this range. So we have nothing to do with this 4, 5, 6, 7, 8, 9 and at all, right? So they will be our max values only in those examples in which the window size exceeds. But in this example, since the window size is fixed and it is of size equal to 3, so our MEX value will also always lie in this range only, that is from 0 to 3. So once this thing is clear, let us now move forward and see how can we solve it for the given constraints, right? So I want you to pause this video and think for a moment, how will you solve this, or what data structure you might need to apply here, right? Because our requirement is very clear that we always want the smallest non-negative integer. So focus on this word, we want the smallest, right? And it should be a non-negative integer. So how will you obtain the smallest non-negative integer? So we can do this using a set. Yes, we can do this using a set easily. But how? Because we know that this set is by default an ordered set, right? So that's why if you put any number of elements, then in the front the smallest element will be present, that is the smallest, and at the last the largest element will be present. So smallest will be present at the beginning and the largest element will be present at the end, because this set is by default an ordered set. So we can utilize this property of this ordered set in order to find the MEX value for each and every window. So let us see that how we will do it. And since I have told you now that we will use a set here, so what we will do is, for every window, since we want an MEX value and we know that our MEX value only comprises of either 0 or 1 or 2 or 3, so what we will do is we will insert each and every possible MEX value into this set, right? Because these are the only possible answer. Out of these 4, no other integer will be our answer for any window, right? And for every window, every time, what we will do is we will take out the value from this set, which will be our MEX value, right? So initially I have pushed all the possibilities here in this set here. So since this will be ordered by default, so that's why 0 is present at the beginning, then 1, then 2 and then 3. So this is my ordered set initially, right? And I have pushed all of my possible answers for any window like this, right? And now let's move forward and let's see how we will use this set that we have initialized here with all the possible max values in order to find the answer, right? So this will be our first window, right? So this will be our very first window. What we will do is we will handle this window separately first, and then the result that we will obtain with this window, we will utilize it in order to find the answer for the remaining windows, right? But since this is the very first window and nothing is computed yet, so that's why we will first go with this window. Now what I am saying is, we will traverse through each and every element present in this range, that is from 1 to k, because this 1 to k is our very first window, right? And we know that whatever elements are present inside this window are actually the elements that are present in the window, which also means that they can never be our max value, because the definition of MEX is itself says that it should be the excluded value which is not present in this window. But if any value is present in this window, then it should never be our MEX value, right? So that's why we will see that the first element we have is this 1. So it means that for the current window, 1 should be present in the window and it should not be our MEX value. But since we have pushed all our MEX values into this set here, which was initially 0 and 1 and 2 and 3, so all 4 values are present. But now we know after traversing this first element that this 1 is coming in the window and it can never be the MEX of this window. So since it can never be the MEX here, so what we will do is we will erase this 1 from this set, right? We have to erase this 1 from this set. So we will erase it because it can never be the MEX for this window. Similarly, we will move forward and then the second element will come. So we will see that our second element here is equal to 2, right? Our second element here is equal to 2, and since this 2 is also present in this current window, that is the first window, so it means that this 2 can also never be the MEX. But since this set here only holds those values which can be our possible max, but now we know that these 2 cannot be the max anymore, so that's why it means that we need to erase this 2 also from this set. So that's why we will also erase this 2. So in this way, when we have traversed both of these elements, that is the first index and the second index, then we have encountered 1 and 2, so it means that they are present in the current window and they cannot be the max value. So since this set only holds those values which can be our answer, but now we know that this 1 and 2 cannot be the answer for this current window, so it means that we need to erase this 1 and 2. So we erased it here. And now we will move to the next element like this. That is the last element of this first window, and then again we will see that the element value for the third index here is equal to 1. So since this 1 is again coming in the current window, so it means that this 1 cannot be the max, so this 1 needs to be erased from the set. So I will try to erase this 1 from the set here, but since it is already erased, so we will do nothing. So in this way, when we have traversed this first window completely here, so then this will be the status of our set, right, in which only 2 elements will be present, that is this 0 and this 3, and this 1 and 2 is already erased after processing the first window, right? And now if someone asks you to find the or print the MEX value for this window, then what will you return? So since we know that this set is an ordered set, so this 0th element which is present at the beginning will be my smallest element, and this third element which is the second element here, which is also the last element of this set, will be present at the end. So only 2 elements are present, this 0 and this 3. This 0 is present at the front, this 3 is present at the last. So that's why I can say that out of the remaining elements in the set, that is 0 and 3, only one of them can be our answer, that is either 0 and either 3. And since this 0 is the smallest one here, why? Because it is present at the front of this set, so that's why it is the smallest here, right? So it means that our MEX value for this window will be nothing but this 0 only, that is the element that is present at the beginning of this set. So our answer for this window will be 0, right? So that's why we will print a 0 in this case. I hope you understood this, and let me also tell you 2 things. So you must be wondering why I have used a count array here and what does this statement mean. So let me tell you this quickly. So as we will move forward, then we know that one element will be added and one element will be excluded, right? So whatever element will be added will be definitely present in the current window, right? So it must be deleted or erased from the set, right? But whatever element will be excluded, so you might think that we need to reinsert it into the set because it is no longer present in the current window, right? But this is not the case. It might still be present in the current window, so we must not insert it in the set. And in order to get that information, we will use this count array, right? And another thing is that I have written here that we would apply set operations only on those elements which are less than or equal to k, and it is true because whatever elements value are greater than k, they have nothing to do with our logic because those elements are first not present in our set, right? Nor they contribute anything to our MEX value. So that's why whatever elements are present and have a value of greater than k, they will not modify our logic. They will not play any role in calculating our answers, right? So that's why whatever set operations we will be applying will be only applying on those elements which are less than or equal to k. So since here this 1 and 2 here in this window, every element was less than or equal to 3, so that's why I have tried to apply the set operations on each one of them. And after applying it, this was the status of my set which only consisted of 0 and 3 because I erased this 1 and 2, right? And after this erasing 1 and 2, the element that was present at the beginning was this 0. So that's why I was able to say that for this current window, this 0 is my MEX value, right? And along with it, when I was moving forward in the first window here like this, I also increased the count for every element here. That is, 1 was encountered twice, so the frequency of 1 became 2 and the count of 2 became 1 like this, right? So this count array only holds the counts of every element greater than or equal to 0 and less than or equal to k, that is from 0 to 3. And why this is important, you will realize very soon as we will move forward with the next windows. So let us move forward now. This will be our second window, right? So this will be our second window, and before our window was this, and now we want to include this nums of I and I want to exclude this nums of I minus k, right? So since this nums of I, that is 0, will be included in the window, so it means that this 0 should not be the max anymore. So if this 0 is present in the set, we need to erase it at any cost. So we will erase this 0 from this set. So I erased it, and before 1 and 2 was already erased, right? Before 1 and 2 was already erased, and now I have also erased this 0 because I have encountered it here. But since this 1 is getting excluded here, so it means that this 1 may or may not be present in the current window, right? So if it is definitely not present in the current window, then it means that we need to reinsert this one into this set. But somehow if this one is still present in the current window, then it means that it can never be the max. So this one should still remain erased. And how we will determine if this one is present or not present in the current window? So we will utilize this count array here. So after we have processed this window, the frequency of the elements will be like this, that is 0 will be coming once, 1 will be coming once, and this 2 will be coming once. So since this nums of I minus k is equal to 1, so we just want to see what is the count of this one. So here the count of 1 will be equal to 1. So what does this one means? So it means that in the current window, this 1 is coming one time, and it is true here. As you can see that this 1 is actually coming one time. So since this 1 is actually positive and it is not equal to 0, so it means that this 1 is still present in the current window. And since this 1 is still present in the current window, then it means that this 1 which you left behind, this element is actually present in this window. And since it is present, it means that it can never be the max. So this one should be erased from this set or should have remained erased. So that's why we will not insert this one back. It will keep remain erased. And that's why this will be the status of my set after processing this second window, right? And that's why since only one element will remain here, which is equal to 3 in this set, which will be the both the smallest one and the largest one, that is begin and r begin. So both are same because only one element are present. So that's why I can say that our answer for this second window will be nothing but this 3 here. That is the smallest one. That is the smallest integer. So I have written the same thing here about this count, that it helps us to decide whether to insert this nums of I minus k into set or not. So if the count is positive, then it means that it is still present in the window and it should not be the max, then it should not be inserted. But if the count of 1 had remained equal to 0, then it means that that element is not present in the current window and can be the max. So that's why we should have reinserted it back into the set. So I hope you got this, why the answer for the second window here is equal to 3. So once the logic for this window is also clear, let us now move forward. That is, we will now deal with the third window. And it is quite a easy one. So see, now we are shifting from this current window to this. That is, we are now adding 5 and excluding this 2. That is, adding the contribution of nums of I and subtracting the contribution of this nums of I minus k. But clearly, since this nums of I is equal to 5, which is greater than k, and we know that any element having a value of greater than k will have no contribution, so it means that we will absolutely do nothing, because this 5 is neither present in the set, neither it is present in this count array. And now we will look into this, that is nums of I minus k, which is equal to 2, which is less than or equal to k definitely. So since this 2 is less than or equal to this k, that is 3, right? It means that we need to do operation on this. Since this 2 is getting left behind, so we will decrease its counter by 1. So earlier the count of 2 was 1 because it was present in the window, and now the count of 2 will decrease by 1. So after decreasing, it will become equal to 0, right? And since it has turned equal to 0, so it means that in the current window there is no element having a value of 2 at least, right? So there are 0 elements having a value of 2. So it means that in this window no 2 is present. So that's why it can be the possible max value. So we might need to reinsert this 2 back into the set. So that's why we will reinsert it here like this. And after reinserting it into the set, this should be the condition of my set or status of my set after processing the third window. And in order to get the MEX value for this third window, we will look the smallest element present in the set, that is the begin element. And since only 2 elements are present here, that is 2 and 3, so this will be present at the front, this will be present at the last. So this will be my MEX value, that is 2. So we will just print a 2 here, right? And in this way our third window is also done, and we will move to the fourth window here. this is our fourth window, and you can clearly see that in this fourth window this one has getting added and this one is getting removed. So this nums of I equal to 1 and this nums of I minus k is also equal to 1, and since we have to add the contribution of this one and remove the contribution of this one as well, so more or less it means that the status of our set as well as this count array will remain same, right? So earlier our count array status was this, that is 1100, so it will remain same because once we increased its count to 2 and then we again decreased its count, so it again became equal to 1. And since this 1 is still present in the window because its contribution is greater than or equal to 0, that is its count, so we will not insert it back into the set. And now again if someone asks you to find the MEX value, so we'll again take the smallest value present in the set, which is this 2, so we'll just print a 2 here, and in this way our fourth window will also be done. Now we will move to the fifth window, which is our last second window, so pay attention. So this is our fifth window, and now we are sliding our window from this current that is the previous window, that is fourth window, to this, that is we are including this nums of I equal to 1 and we are excluding this nums of I minus k equal to 0. So we want to add the contribution of this 1 and decrease the contribution of this 0. So since both of these elements, that is nums of I and nums of I minus k, are less than or equal to k, right? So we will first update their counts here. So earlier the count was like this, and now the count will become equal to this, that is the count of 1 will increase by 1, so it will become equal to 2, and the count of 0 will decrease by 1. So earlier the count of 0 was equal to 1, so now it is equal to 0. So since this 1 was getting added to the current window, so it means that it should definitely not be present in the set because it will never be the max. So this 1 must be erased from the set or should be remain erased. But this 0 which was getting excluded from the current window might or might not be present in the current window. So we will see its count in the count array. So the count of 0 equal to 0, which means that 0 is not present here. And since 0 is not present here, so it means that 0 can be our possible max answer. So we will insert this 0 into the set back. So we have inserted it here. So that's why the set status was before like this, and now we have inserted 0. So 0, 2 and 3, that is total 3 elements are now present and only 1 is absent, and that's why this 0 is the smallest here and this 3 is the largest here because it is sorted. And that's why the MEX value will be nothing but this 0 because it is present at the front. So we will print a 0 here. And by doing this we will move to our last window, that is the sixth window. So this will be our sixth window, and now we are sliding our window from the previous window like this into this, that is adding the contribution of 0 and subtracting the contribution of this 5. But since this 5 is definitely greater than k, that is greater than 3, which means that we don't have to do anything with this 5. So we only need to do our set operation with this 0. So since this 0 is getting included in the current window, it means that it should never be the possible max answer. So it must be remain erased from the set. So that's why we will erase this 0 from the set. So before the status of set was this, that only 1 was erased. But now since 0 was added here, so this 0 will also be erased and only these two elements will remain. And out of these two elements, this will be the front one and this will be the last one, that is this will be the smallest and this will be the largest. And since we want the smallest non-negative integer, so that's why we will pick the front element here, it is the begin element, so we will print a 2 here. And now for this last window we don't need to look anything into this count array. Why? Because we need count array only to see if we need to reinsert this nums of I minus k into the set or not. But since this nums of I minus k here is 5, which is greater than k, so that's why we are not worried about this count array for this last window. And in this way we printed all of our answers. So what things we printed? So we printed first 0, then 3, then 2, then 2, then 0, then 2. So we printed these integers 0, 3, 2, 2, 0, 2. And if you see the expected output also in the problem, then it was same, that is 0, 3, 2, 2, 0, 2. So this was the whole logic in this problem. I hope you got everything here. Let's now look into the code here. So this will be our code, right? So let me explain you everything line by line. So first we will take the input of this n and k, then we will take the input of this n integers in one based indexing type, right? So that's why I took the size here of n plus 1. Then I have initialized a set here which will be holding all the possible max values, that is from 0 to k, right? So that's why I have inserted every possible max value in this set like this, and then here I am handling the first window. So for the first window I am traversing from 1 to k, and whatever elements are less than or equal to k, only in that we are worried, right? So since they will be coming in the current window, so I need to erase it from the set. So that's why I am erasing those elements from the set, and also I am increasing the count of those elements of the current window by 1, and I have initialized this count array here so that it will be helpful in our remaining windows, right? So this count array has nothing to do with this first window. It will only be helpful in the remaining windows. And after the first window is completed, whatever the set is holding at the front will be our smallest non-negative integer, that is the MEX value. So we'll just print that. And for the remaining windows, we will move from k plus 1 to n, right? And this nums of I will be my next element, and this nums of I minus k will be my previous element. So we will apply operation on the next element and then on the previous element if and only if they are less than or equal to k. Otherwise we are not worried. So for the next element, if it is less than or equal to k, then it means that it is definitely coming in the current window, so it must not be the MEX value. So we need to erase it from the set. So that's why we are erasing it here from the set like this, and increasing its count also. And similarly for the previous element, if it is less than or equal to k, then it means that we'll first decrease its count, and then after decreasing its count, if it becomes equal to 0, then it means that this previous element is not present in the current window anymore. So in that case we will reinsert it into the set. But if the count of this previous element is positive, then it means that it is still present in the current window, which cannot be the max value. So in that case we will not insert it back, right? But here if the count is equal to 0, then it means that the current window is not containing this previous element anymore. So we will insert it like this. So after applying operation on both of these elements, whatever element will be present at the front, that is this, that is star st.begin, we will simply print that and return. And in this way we will be handling our remaining windows. So this is our code. So I think I have explained you each and everything in very detail, right? So yeah, this is the logic for this problem. I hope you got everything correctly. So yeah, thank you so much for watching this video. Thank you.